Okay, so this chapter 12, is about acids and bases. We have learned a lot about this already, so a lot of this should be pretty review, such as the difference between strong acid and base. We'll review it just in case it's been a while. And then talking about the pH calculations. I can't remember if we did those yet in the class. We might not have, so we'll look at pH calculations. We will not look at pOH calculations. We'll just talk about the pH and the difference between the strong and weak acids and bases. We'll talk a little bit about a titration, and we'll talk about what a buffer is. Okay, so there are two ways to define an acid and a base. The first way is the Arrhenius way of defining acid and base, and this is what we've been using so far throughout the semester. It's really any compound that forms an H+ ion as its cation is what we considered as an Arrhenius acid. Arrhenius was a scientist, I think, back in the 1800s, and this is kind of what he came up with as to what an acid is. And when we name acids, this is kind of what we look for. We look for a molecule that has a hydrogen in front of it. So if it's H and then like something else, we consider it an acid. And when we throw it in water, it ionizes into H+ ions and Cl- ions. So that's what we have been calling an acid. So it's an ionizable hydrogen. Many acids have just one ionizable hydrogen, but there are some that have more, like sulfuric acid and phosphoric acid. For every mole of phosphoric acid, you get 3 moles of H+ ion. Okay, so that's what we call an Arrhenius acid. An Arrhenius base is anything that ionizes and it produces hydroxide ions. So in the formula of the compound, you have a hydroxide ion. So like sodium hydroxide or potassium hydroxide or even magnesium hydroxide. That's the structure, magnesium hydroxide. All right, these are what we call, again, Arrhenius acids and bases. So it's a process in which hydroxide ion is in the formula. Okay. However, there are other compounds that don't have H+ or hydroxides. Like an example is ammonia. Ammonia is NH3. This is ammonia. Okay. And if you determine what the pH of this is, ammonia is a base. It's basic. Its pH is roughly around 9 to 10. All right, so we know that on a pH scale it goes from 0 to 14, with 7 is right in the middle, which is being neutral. Right, anything less than that is acidic. It means I have excess H+ ions. Anything to the right of it or above it is basic, and it means I have extra hydroxide ions. Okay, well, ammonia is actually a base. Now, ammonia, I guess you could say, looks more like an Arrhenius acid because it has the H's. It does not have a hydroxide in the molecule. So how can this be a base? According to Arrhenius, if it has hydrogens, it's an acid. If it has hydroxide, it's a base. But this is a base, but it does not have a hydroxide. So Arrhenius was not able to, with his way of how to define acids and bases, he cannot explain this with the way that he has a definition. So Bronsted and Lowry, doesn't have Lowry's name in here. I don't know why. I've never seen that before, but it's usually a Bronsted and Lowry acids and bases. Okay, so several years later, they came out, Bronsted and Lowry, and said that they actually had a different way of how to define acids and bases. So how they defined it is with respect of the proton or the hydrogen atom. What's happening with just the hydrogen atom? Okay, it wasn't hydroxide and the hydrogen. It was just basically the hydrogen. So anything that it donates a proton, they called an acid. So if you donate a proton, like for example HCl, okay, it gives away a proton. And a base is anything that accepts a proton. All right, so if you take HCl and you add it to water, okay, what happens is you form H3O+ and Cl-. Okay, so what's happened is the HCl It gives its proton to water. It donates. So this is donating a hydrogen, donating an H+. And what's the water doing? Well, the water is accepting the H+. Right? Because in my products, I have H3O. So I went from H2O to H3O, and I also gained a plus charge. Why did I gain a plus charge? Because this H is traveling over here as an H+ ion. So it brings an extra hydrogen, plus it brings its plus charge as well. And Cl is neutral over here. It's losing the H, and it's losing a plus charge, so that's why it becomes a negative charge. Okay? As far as the acid and base is concerned, notice HCl is donating its hydrogen. So anything that donates the proton, we call the acid. So this HCl is called the Bronsted acid, or the Bronsted-Lowry acid. I'm going to put a Bl acid. And the water is acting as a Bronsted-Lowry base. So they basically said in every reaction, you have both a Bronsted acid and a base. Okay? So every reaction, it doesn't matter if it's HCl, if it's like sodium hydroxide, if it's over here it's showing ammonia and hydrochloric acid. So ammonia and HCl. So what's the ammonia acting as? So here are the products. So is the ammonia accepting or is it donating a proton? In the chat box, why don't you put A for accepting or put B for donating? What's the ammonia doing? Accepting or donating? Accepting, exactly. So the NH3 is accepting a proton. Okay? So therefore, the ammonia is acting as a base. All right? And the HCl, the hydrogen is donating its hydrogen to the HCl, so this is acting as the acid. All right? So the ammonia becomes the ammonium ion. It gets an extra hydrogen, and it also gains that plus charge from the H+ that moves over there. Okay? Now, on the other side of the equation, we actually have names for these. Okay? This is what's called the conjugate, and I think the next slide it talks about this, but I'll talk about it here. This is the conjugate acid, and this is the conjugate base. All right? So how do we know what you call the acid and base? There are two ways. The right way is to look at the reaction in the reverse direction to see what's going on. So imagine the reaction is going from here to there. Okay? So notice that the chloride is going from a Cl- to an HCl. So it's accepting this proton back in order to go that way. So if it's accepting the proton in order to go backwards, it's acting as the base. The ammonia, it donates its proton. So therefore, it's the acid, it's the conjugate acid. So that's how you know. But the other way is whatever the ammonia was on this side, on the opposite side, it's the exact opposite thing. So the NH3 is part of the base on this side. Therefore, the NH3 is part of the acid on this side. The chlorine is part of the acid on this side. Therefore, it's part of the base on that side. So that's how you know also what the conjugate acid and base is. Okay? Okay, so let's go back to the ammonia example. And what Bronsted and Lowry explained was, well, when you take ammonia and you put it in water, you actually have a chemical reaction. Nothing's really ionizing in this case. Okay, they basically said nothing really ionizes. What happens is the hydrogen actually is transported onto the water. This is actually what acid is. It's H3O+. It's not H+ ions. These don't really exist. They spell exist. That's not how spell exist. That is. An H+ ion is not really a real thing. It actually exists as an H3O+. So when you have these reactions occur, it's actually the hydrogen is going on the water molecule. Okay, so it's not really ionizing. It's just transferring onto there. And as soon as you form H3O+, that's acid. Okay, so in this case, what they said is happening is the ammonia is plucking off a hydrogen off of water. So in this case, water is acting as the acid because it donates a hydrogen to the ammonia. Over here, it's acting as a base because it's accepting the proton. So if hydrogen is giving up its proton, look at what we're forming. We're starting to form hydroxide ions. So this now explains pretty much every acid and base. Arrhenius was only able to explain things like this, that have an H on it or have an OH. Bronsted now can explain everything. It explains that it's really not ionizing. What makes an acid is the formation of this. If you start forming this, then you have an acid. If you start forming this, then you have a base. Okay? Notice also something interesting, which I think we talk about in a later slide, but I'll give you a heads up. Notice that water can act as both an acid and a base. All right? This is what's called amphoteric. All right? I find it funny I can spell amphoteric with no problem, but I'm not sure about how to spell exist. I just find that amusing. Anyways, amphoteric means it has both properties. Okay? Or like both of the opposite properties of that thing. So it's amphoteric because it has both acid and base properties. All right, it comes from the word amphibian. Amph means it has both properties. So amphibians, they can breathe in water and they can breathe outside of water. So water is what we call amphoteric because it's actually acid-base. But if you look at water, here's the H plus part of it, and here is the hydroxide part of it. So if they come together, it neutralizes them for water. If you split them apart, you have more of one or the other, then you have an acid or a base. All right, so it's really water is our solvent here, and it either gains protons or it gets hydrogens plucked off of it in order to become a hydroxide. Okay, so
Justin, I got a question.
Sure.
So if water can act as an acid or a base, do we have to look at what the other part of the reactants are to figure out which it does?
Yeah. So that's a great question. If you have a reactant, so I don't know, reactant A, and you're reacting it with water, you have to look at this and figure out how is water acting it. If I'm adding like HCl to it or HNO3 or something like that, then it can act. In this case, it'll be acting as a base. Yep, exactly. Okay, so here...
Sorry, I have a quick question.
Yeah, sure.
Well, that last slide.
Yep.
For, it said the conjugate acid is the NH4 plus, and the conjugate base is the Cl minus.
Right.
Are the other ones the opposites as well? They just didn't write them on there?
Yeah, exactly. Yep, yeah, that's a good question. So our hydroxide here is a conjugate base.
Okay.
Conjugate base, and then the H3O plus here is the conjugate acid. Yep, exactly.
Okay, thank you.
Yep, you're welcome. Okay, so this is just kind of a problem just to make sure that you understand how these charges work and how everything works. So if you have HNO3, what is the conjugate base of HNO3? All right, so that would imply that you're losing a hydrogen off of this. Okay, so that would imply it's acting as an acid. So the conjugate base of this, so if it's acting as a conjugate acid, it donates its hydrogen away. So its conjugate base would be NO3 with a minus charge. Does that make sense? Because, so this is the acid form. This would be our conjugate base form. Okay? So anytime it asks for a conjugate base, you have to lose a hydrogen. If it asks for a conjugate acid, you have to put the hydrogen on. So in order to get the conjugate acid of this becomes HO2, or also known as H2O. I've never seen it written as HO2, which is kind of weird. Oh, yeah. I don't know what that is, because it's not H2O, it's HO2. Anyways, that's what the conjugate acid of this would be. This is not a correct thing. This should probably be a 2 here, but that's probably an error. But anyways, that is exactly how it would go. So why don't you do it for these two? Show me what the conjugate base. I have a feeling this is supposed to be a 2 minus, that 2 is supposed to be there. So let's actually do that instead, because this does not make any sense. So O2 minus, its conjugate acid would be, I'm adding 1 hydrogen to it. So it would be HO with a minus charge. Okay, because remember, I'm adding an H plus to it. So I add an H, and one of these pluses cancels out one of the minuses. Okay, so that's what I think that's supposed to be. I think that 2 was supposed to be up there. Okay, so why don't you do the same for these? Show me what the conjugate base form of this would be, and show me what the conjugate acid form of that would be. I'll give you a little bit of time to work on that. Okay, so the conjugate base form of this would mean that this is acting as the acid, so it's going to donate the proton, so we're going to get SO4 with a 2 minus charge. Everybody get that? And then the conjugate acid of this would mean that I'm adding the proton to it. So it'll be H2CO3. Alright, so up here I'm getting rid of an H plus, so an H plus is leaving. So this H is leaving with one of its pluses, so that means it makes this more negative. This, I'm adding an H plus to it, so we make a second hydrogen, and then this plus cancels out that minus, and I get H2CO3. Okay, make sense? Okay. And here are the answers, which we already did. Okay, I'll go over this with you guys, but just to kind of practice as to labeling conjugate acids and bases. So the HF, and I have NH3. So if you're not too sure as to which one's the acid and base, look at the products. However, this should be kind of obvious because we know now that ammonia is a base. Now, it might not always, because ammonia is also kind of these amphoteric type molecules. It can either accept or donate, but most of the time it's going to act as a base. But HF, we know. All right, you know that's hydrofluoric acid. All right, that cannot act as a base. Okay, so there are certain molecules you absolutely know without a doubt will always act as an acid. Okay, especially any of the strong acids like hydrochloric acid, hydrobromic, nitric, sulfuric, any of those will always act as an acid. However, if it's like H2PO4 minus, that can act as both. Because it can still accept the hydrogen and get rid of that plus charge, or it could lose another hydrogen and gain a 2 minus. But like H3PO4, that can only lose a hydrogen. You can't do anything other than lose a hydrogen. Or if I have like PO4 3 minus, that can do nothing but, the only thing you can do is gain a hydrogen. Because I don't even have any hydrogens here to actually lose. So these are no doubt as to what they do. But if you have anything in the middle, if it has hydrogens and a charge to it, it can do both. All right. So I just kind of want to point that out. So in this case, you can see that HF is becoming a negative charge, so it's donating its hydrogen. So this is acting as the acid. The ammonia is gaining the hydrogen, so it's acting as the base. So the F minus is the conjugate base, and the NH4 is the conjugate acid. Also, kind of a rule of thumb, but not necessarily 100% of the time, but probably 99% of the time. If something has a negative charge, it's pretty much going to be the base. If anything has a plus charge, it's going to be an acid. Why is that? Well, if something has a plus charge, it wants to get rid of a hydrogen. Okay? If something has a negative charge, it wants to accept an H plus in order to get rid of that negative charge. So over here, without even looking, I pretty much know this will probably act as the base, since I know water is both an acid and a base. But since this is a negative charge, this is pretty much going to act as the base. And just to double check, you can actually see that it is accepting a hydrogen, so it is the base. So there's little clues that you kind of have to look for in each case in order to figure out what is the acid and the base. There are some where it's very obvious. HF. H3 or PO4, or PO4 3 minus. Those are obvious choices because I don't have any hydrogens here, so it has to act as a base. But when you have things like this, it can act as both. You have to look at the other thing. Okay? So, like if you had H2 PO4 with a minus charge, and you're reacting it with, let's say, O2 minus, let's say. All right, what does this have to be acting as? Now, you notice they both are negative charges, so everything I just said up here, I can't look at this where I have a negative and a positive. They're both negative. However, this is the only thing that has hydrogens. This, I can't donate a hydrogen from O2 minus, right? So this has to act as the acid. I don't have any other choice. That means, so therefore, this has to act as the base. All right. So our product, I'll tell you what. Why don't I put this on pause? You guys predict what the products would be, and then tell me what's the conjugate acid and what's the conjugate base. So this is acting as an acid. One of these hydrogens is going to come over to here. All right, so it's going to lose a hydrogen. So this becomes HPO4. And if it loses a plus, it's going to become more negative. So this becomes a 2 minus charge. Also, I don't know if I stated this. I've shown it, but only one hydrogen ever moves. All right, you don't have more than one hydrogen move. All right, technically both of these hydrogens can move over, but always only have one. So if this now gains a hydrogen, it becomes HO, and then that one, and then the H plus, this plus will cancel out one of the negatives, so this becomes a minus charge. So this is going to become your new molecules. This will be the conjugate base, and this, believe it or not, is our conjugate acid, which is weird to see a hydroxide as an acid, but in reality, this would not actually do it, but this is not reality. Nothing about the past several weeks is reality. Okay? So does that make sense? And then up here, just to kind of finish this, this is going to be the conjugate acid, and this is going to be our conjugate base. Okay? So the types of problems I would give you, if it's pretty obvious as to what the acid is, like if I give you H2SO4 plus, ammonia, all right, I don't have to tell you what the products are. You know what the acid and the base is, or you should know. Okay, this is sulfuric acid, so that's the acid. Ammonia we know is the base. But if I give you something, and again, here you might not know what the acid or the base is, but it's kind of obvious as to what it is because this is the only one that has hydrogens. Okay, so that's kind of obvious. But if I give you two compounds, which might not be obvious, like maybe like these two, then I would have to show you what the products are. Okay, or I would tell you this is the base. Okay, but you could figure it out in this case since I have the negative charge here. Again, anything usually, especially if I have water, if I have an amphoteric molecule, and the other thing has a negative charge or a positive charge, I know exactly how this is reacting. Okay? Okay. So, all right. So, 12.3 is, any questions up until now before we go on? Okay, good. Okay, amphoteric. I just talked about this. Basically means has both acid and base properties. So here's an example just showing that water is amphoteric. It acts as an acid and a base. Okay. There's these chemical formulas. These mathematical formulas that we'll talk about. This kind of shows what's called the auto-ionization of water. Water actually exists. So if you have a glass of water, it actually exists as H3O plus ions and hydroxide ions. And this is the concentration. Very, very, very small amount. So if you think about the 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's the percentage of H3O and hydroxide ions floating around in water. Okay, honestly, I have no idea how they figured this out, but they did. Okay, so this is one of the equations. These brackets mean concentration. It's concentration. Okay, so I believe it's in molarity, but they don't state it. Okay, So this equation we're going to use. So, like for example, if you ever want to find the concentration of H plus ions of a solution, this is the formula that you will use. All right, we'll kind of do problems with this as soon as we start talking about like the pH calculations. Okay, so I'm going to kind of just skip through this and we'll talk about it when we get to the pH calculations. Okay, why don't we take a quick break right now? Let's take like about a 5-minute break, and then when we come back, we'll start with the strong acids and bases. Okay, so strong acids and bases. So we talked about this before the break, but pretty much a strong acid or a strong base are any acids and bases that ionize 100%. We also talked about this when we talked about electrolytes. We talked about a strong electrolyte and a weak electrolyte. The strong electrolytes were the ones that ionize 100%. The weak ones partially ionize. Okay, so the strong acids completely ionize in water. Okay, so hydrochloric acid is an example, which basically implies that, so hydrogen is, HCl is actually a gas. But when you put it in water, the H from the hydrogen actually transfers over into the water, and you form the H3O+, and you form a Cl- ion. Okay, and then a strong base. So basically, what happens is every molecule of HCl that comes out of the tank completely ionizes and forms the ions. With sodium hydroxide, same thing. So this is actually a solid. It's a white solid, and we throw it in water, it just completely ionizes and it dissolves. Okay. So that's basically strong acids and bases. Like I said, I don't want to do these problems yet until we go over to it. Let's actually do the list. I thought they actually had a list here. But the list, so strong acids, actually I know they have it on another slide. But we'll go over here. HCl, HBr, HI, HNO3, H2SO4, and HClO4. Let me check. I always get that one mixed up. It's either HClO4 or HClO3. Let me just double check real quick. Yes. Okay, so those are the strong acids. Anything other than these acids is considered a weak acid, so they partially ionize it. So like hydrofluoric acid is actually considered a weak acid. Only a portion of it ionizes. Acetic acid, which is HC2H3O2. That's acetic acid from vinegar. That's also a weak acid. So pretty much any other acid, phosphoric acid is considered a weak acid. These are all examples of weak acids. These are the only 6 strong acids. Everything else is weak. Okay? Okay, so like I said, these calculations we will do in a bit. But I do want to talk about pH calculation. All right? The pH, and we're not going to worry about the pOH calculation. But the pH calculation is how to find the pH of an acid. All right? Or a base. So remember, the pH ranges from 0 up to 14. Okay? And the equation is the negative log of the H plus ion concentration. Okay? Now remember, we also have this equation, which I said don't worry about. Well, we're going to start worrying about it right now. This is the auto-ionization equation that we just talked about in the previous slide. So with these two equations, you can actually do pretty much almost all of the calculations in this chapter. There's also another one which we'll talk about, which is the antilog. All right, but this is how you can find the pH of a concentration based on the concentration of the H3O plus concentration. Okay, so for example, if this is my acid concentration, so this is H3O plus. That's the concentration of my acid, the 3.5 times 10 to the negative 4th. In order to find the pH is the negative log of that number, 3.5 times 10 to the negative 4th. Okay, so if I put this in my calculator, do it real quick. Hold on 1 second, I gotta go grab it. Okay, so you do the negative log 3.5 times 10 to the negative 4th. And take the log of that. So you get 3 point, you get a pH equal to, I'll round it up to, well, 3.46. Okay. So I want to talk a little bit about logs. A lot of people kind of get a little bit afraid of logs. They're not quite sure what they even mean or how to handle them. It just depends on your math teacher. I'm going to make this very simple. A log is basically how big your number is. It's the extent of how big your number is. It's the power on the 10 of the number. So, for example, if you have the number 1,000, okay, if you were to transform this into scientific notation, it'd be 1.0 times 10 to the third. Okay, because if I move this over 3 places, I have 10 to the third. If I were to take the log of this number, the answer is 3. Because this is basically what the log is telling me. The log is telling me the extent of how big this number is. Right? It's telling me, well, how big is the number? Well, the number is in the thousandth place, so therefore the log is 3, meaning that the number is around 1,000 or in that 1,000 area. So if I had a number like 4,568, the log of this is not exactly 3, but it's going to be somewhere around 3. All right, it changes it. These values are going to change that a little bit. But if I were to write this in scientific notation, times 10 to the third, the whole point of log is kind of telling me roughly how big this number is. All right, now this 4, the 5, and the 6, and the 8 are somehow factored in the number, but I know the answer is somewhere around 3. It could be like 2.8 area. It could be like 3.4 area. It's somewhere in this range, but I know it's somewhere around 3 because the log is basically what the power is. So if I were to actually do this, let's actually do this. 4, 5, 6, 8, and take the log. The answer is 3.6. That's what the answer is. Okay? All right, this you actually need a calculator for, but you kind of know approximately what the answer is, all based off of our power. Okay, so over here, I have a power of 4. Okay, so I knew my answer should be around 4. All right, it might be a little bit lower than 4, which it was, is 3.46, or it might be a little bit higher because this 3.5 affects that number a little bit. But I know approximately where it should be. Okay, and that's basically all a log is. A log is basically telling the reader approximately how big our number is. In this case, it's a negative log because if I were to take a log of a negative number, I get a negative value. So I'm multiplying it by a negative number in order to get a positive number. Okay, does that make sense? I have to do a negative in order to get the positive. So just by looking at this number, roughly what is the pH? Why don't you just write it in the chat box? You don't have to calculate it. Yeah, it's roughly around 7. Exactly. How about this one? What is it? Yeah, it's roughly around 11. Right, because of that 11 there. Yep. All right, I got you, Kayla. All right, now this 8.8 will change it a little bit. I believe the higher this value is, this will go higher. But let's just double check it. So if you take the negative log, so 7. Oh, I know. I can't find my calculator. My kids hid my calculator. So I gotta use this stupid thing. So it's actually 6.77, which is pretty close to that. 6.77. And then if we do this one, so 8.8. It's 10. Okay. So yeah, it's not exactly 11. If this was 1.0, and then that, it would be. No, you know what? I did that backwards. The larger this number, the smaller that number, because this number implies it's getting larger, so it's getting closer up to the 10, up to the negative 10. Does that make sense? So like if I have 0.009, right, that's almost 0.01, right? So this is times 10 to the negative 3. This is times 10 to the negative 2. So this is close, like to 10 to the negative 2. So its pH of this is probably around like 2.4 or 2.5. So let's actually do it just to kind of show you. Again, so I'm just kind of showing you a way that you can actually predict this. So 0.009, take a log of that. Yeah, it's 2.04. All right, it's pretty close to 2. Okay, so I hope that helps as far as logs are concerned. A lot of people are afraid of logs. They take math, and math instructors sometimes confuse them even more. Be like, I don't even know what it is now. But that's all a log is. So if you have any number, write it in scientific notation, and you can roughly predict what the log of it will be. Okay? Okay. Now, this is the opposite. This is, rather than, so in the previous problems, we were finding the pH, and we were given the H plus concentration. We were given this. In this case, we are given the pH. This is what we're given, and we're trying to find the H plus concentration. This is what we're trying to find. Okay. Well, remember what I just told you. The pH is the power of 10, or I'll call it on 10. It's the power on 10, right? So if I gave you like 10 to the third, its pH is 3. Okay, well, how did I get that? Because that number is the power. So that's what these are. These are the powers of 10. Okay? By the way, that's what this P means, power of. Okay? So the way that you find the H plus concentration is you take 10 and raise it up to that value, 4.76. And actually it's negative, right? Because everything is a negative. So you take 10 raised to the negative, so and you get 1.74 times 10 to the negative 5th. Okay? So it's basically, I can't keep it as a decimal point. I have to make it into an actual value. Where if you notice, these numbers are pretty close to the same because that's the way it works. I mean, it's basically a power of. Okay? So if you're given a pH and you want to find the H plus concentration, it's what's called the anti-log. And what you're doing is you're just taking these values and raising them up to the negative power. Okay? So the three equations that we have so far is the pH equals negative log of the H plus concentration. We have the anti-log. So we have the H plus concentration is equal to 10 raised up to the negative pH, which is the opposite of that. And the other one we have, which I'll show you how this will apply. 0 times 10 to the negative 14. So these are the three basic pH and hydronium ion equations that we have. Okay. So let me see if there's issues determined. So these questions on the POH, we aren't going to do any of those. Okay, so don't worry about the POH. It's not that common to actually find a POH. Okay, so let's actually do. Let's erase these. Let's say I give you what is the pH if the hydroxide concentration is equal to 6.37 times 10 to the negative 8th. Okay, I'm going to write these equations over here. And you have to figure out which equations you're going to have to use to figure out this problem. Okay, now it might be more than one equation. It might not just be one equation. You might have to use one to solve one answer and then plug it into another one. So I'm kind of giving you the hint there as to what you got to do. Okay, so 1.00 times 10 to the negative 14. So I'm giving you the hydroxide concentration. I want you to find the pH. So notice, in order to find the pH, you need to know the H plus concentration. When I don't give you the H plus concentration, what do I give you? I give you the hydroxide concentration. Well, can you find the H plus concentration given the hydroxide concentration? I hope you're shaking your head. Yes, I can do that. Okay, so I'll give you a little bit of time, a few minutes, to see if you can figure out this problem. Okay, so this has got to be plugged into this equation. So you'll have H plus equals 1.00 times 10 to the negative 14th divided by your 6.37 times 10 to the negative 8th. All right, and that is going to equal, let me type it in real quick. Oop. Should have done this before. So I get 1.57 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. Does that sound right? And then we take the pH of this, which is the negative log of 1.57 times 10 to the negative 7. .8. Which is what I expect, since this is about 7, so I'd expect my number to roughly be close to 7. All right? All right, Kayla, nice. Sound like you were excited you got it. Okay, and that's basically how you, yeah, it's a lot of math. The trick, just to make sure, is especially right here, is when you divide this, make sure you do this either in parentheses or use that EE button. Okay? If you don't remember how to multiply, and I made a mess of that. If you don't remember how to multiply and divide your powers, all right, when you multiply powers, you add them. So if you like 10 to the 3rd times 10 to the 6th, the answer is 10 to the 9th. All right, if you divide them, 10 to the 6th divided by 10 to the 3rd, the answer is a subtraction. Okay, so if your final answer here, instead of -7, if it came out to be like 10 to the, I don't know, 23rd, minus 23rd, or minus like 22 or something, that means that this was actually on top and it got added. Okay, so if in doing your problem, so I mean, I don't know exactly how you did it, but if you got something like this, that's what happened. It did not go on the bottom. So you have to be careful of that. Okay, so again, you can kind of predict what your answer roughly should be by just taking the 14 and subtracting the 8. I mean, obviously that's 6, but you know it would be somewhere 6, 7, around there. So in this case, it's -7. Okay, so if that's what the issue was in doing this, if you're like, I got some incredibly small number, that's what happened. All right. Okay. Okay, good. So those are the types of math problems in this chapter. So just kind of an idea, if you understand this, you can manipulate these equations. That's basically how you do it. Okay. Another way I can ask you is I give you the pH. I'll say that the pH is 4.7. What's the hydroxide concentration? So what you do is plug in the pH here, solve for H plus concentration, plug H plus into here, and then solve for the hydroxide concentration. So that's kind of how you can use like two of these equations in one problem. Okay, so let's now go to weak acids, if there's no questions on that. A weak acid is basically, as I said, it's something that partially ionizes. The double-headed arrow, see how they're showing you a double-headed arrow here? Okay, this implies what's called an equilibrium. Next chapter, chapter 13, we talk about equilibriums. Hopefully I can get to a portion of it, but I mean, I'll try to at least I talk a little bit about it. But I am going to talk about what an equilibrium is now, so you are kind of getting a portion of chapter 13. Most reactions are actually in an equilibrium. An equilibrium is where I have two compounds. In this case, I have HF and water. Okay. What happens is the HF starts donating its H pluses onto water and forming F minus and H3O plus ion. At a certain point, at a certain concentration, what happens is these compounds then start reacting with themselves. And the hydrogen, the H plus ion, donates its hydrogen back to F minus to actually reform HF and water. Okay? And then as that's happening, more HF and water are reacting to form F minus and water. And then as soon as I form a certain amount of this, it goes back and reforms. And as soon as the rate of this reaction, our forward reaction, is equal to the rate of the reverse reaction, that means for every mole that forms F minus and H plus, the same amount of moles form HF and H2O, we are said to be called at equilibrium, and where we have equal amounts from our reactants to products and our products and reactants. And it's not exactly at 50-50. It just all depends on a reaction. It could be like 20-80, or it could be 80-20, or it could be 1-99, or it could be 99-1. Every reaction is different. In chapter 13, we learn how to find out what those values are. But for right now, I just kind of want you to understand what equilibrium is for a weak reaction of some sort, in this case a weak acid. For every molecule that forms the product, a product molecule reforms the starting material. Okay? Initially, if I don't have any of my starting material, my product, obviously it reacts and reacts and reacts until it hits that concentration at which it starts going backwards. And then when the forward and the reverse are equal, I'm at equilibrium. And that's what a weak acid will do. Only a portion of this is actually in the F minus form and the H plus form. But the majority of it is still in this form right here. So here they kind of show you that the HF, here's an HF molecule, HF, and I'll circle them. These are HF molecules that have not ionized. Now remember, what makes acid? What makes acid is this, H3O plus. This is what makes acid, not the HF molecule. It's the formation of the H3O plus. So the more H3O plus I have, the more acidic. Okay, if I have a very small amount of H3O plus, I might have tons of HF. I might have tons and tons of HF, but I might have a very small amount of H plus ion. Therefore, my pH is, is pretty close, like to 7. It could be like at 6.5, because my pH is just all dependent on how much of this I have. Remember, it's based on the H plus ion concentration. The more of this I have, obviously, the lower our pH. Okay, so a pH of 1 or 2 or something like that. The less H plus ion I have, the more I'm around a pH of 6. Okay, so weak acids usually have a pH roughly around 5 or 6. Like vinegar, for example, I think the pH is about about 4.5. All right, pH of 4.5. Hydrochloric acid, strong acid, it's like a pH of between 0 and 1. So just to kind of give you an idea. All right, so vinegar is like 1,000,000 times, or I'm sorry, hydrochloric acid is 1,000,000 times more ionizable than vinegar is. Okay. So that's basically what a weak acid or base implies. It's where it partially ionized, but most of it exists in this form. And remember, this is what makes it acidic. All right, these ions is what makes it acidic, not not these HFs in here. Okay. Any questions on that? Okay, so here they just kind of give you a partial list of weak acids, and then here's a list of strong acids, which I went over. I showed you. Oh, you know what? You know what's interesting? Both perchloric and chloric acid are the strong acid. Maybe that's why I always get them confused, because they both are. So I'm actually always right. Even when I think I'm wrong, I'm always right. So notice that they have chloric acid and perchloric acid as strong acids. So HCl, HBr, HI, nitric acid, and sulfuric acid. And then they have both the perchloric and the chloric acid. Okay, so there are 7 strong acids. All right, everything else is weak. Acetic acid, benzoic acid, formic acid. This is the acid in fire ants. So when fire ants inject you, it's formic acid. Nitrous acid, hydrochloric acid. Okay, we are not going to be doing the pH calculations of weak acids and bases. They aren't that straightforward, so we are not going to be doing this. And then here's a weak base, basically the same thing. It's in an equilibrium. Ammonia is an example of a weak base. Once you form a certain amount of ammonium ions, hydroxides start reacting with it to reform ammonia and water. All right, so most of it exists in this form, and we have a very small amount of the hydroxide ions. Okay, again, here are examples of some weak bases. Here are the examples of the strong bases. Notice it's the 1As, sodium, potassium, and lithium. Remember, those are the 1A metals. And then we have all of the 2A metals: barium, strontium, and calcium, rubidium, and cesium. Actually, these are 1As. These are not very common. They are strong, but they are not the common ones. So these are the 6. If you remember on the solubility chart, if you look back at the solubility chart from the reactions lab when we did the precipitation reaction, if you look at the bottom of the solubility chart on the hydroxides, everything is insoluble, which means they are weak. Okay, with the exception of 6 of them, and these were the 6. I don't know if you guys remember that, but if you look back, you'll see that. Okay, same thing. We're not going to be doing pH calculations of weak acids and bases, just of the strong ones. All right. All right, I think we are going to call that